Hello folks, welcome to a short video about the relationship between integrals and areas. Now to be sure, at this point in this video series we have not even defined what an integral is. That's coming soon. However, we have spent quite a bit of time talking about areas. Indeed, we built Riemann sums to approximate the area under a curve. And so first, a quick review of what happened in the previous section. We built this thing called a Riemann sum for a function f on an interval ab. And there's more than one Riemann sum. You have some choices you can make, right? You can choose whether to use right endpoints or left endpoints as the evaluation points, or something else for that matter. You can also choose how many rectangles you use in your approximation. So a little summary, this is what the Riemann sum looks like, right? So here is our summation notation. We take the function at the kth evaluation point that gives us the height of the rectangle, and delta x is the width of every single rectangle. Notice that delta x doesn't depend on the counter k. It's constant because we construct our Riemann sums using what are called regular partitions. A regular partition is one in which all the subintervals are exactly the same size, namely b minus a over n. And indeed, there it is, right? Delta x is b minus a over n. That's the width of every rectangle subinterval in a regular partition. And as I said a moment ago, CK is the evaluation point in the kth subinterval. So we will almost always choose CK to be the right endpoint or maybe the left endpoint. In theory, though, it could be any point in the kth subinterval, and you could even choose them differently from subinterval to subinterval if you wanted to. But we're not super interested in Riemann sums per se, so we won't go to that level of complexity. And we noted above, indeed, this is why we built the Riemann sum, that for a positive function, the sum approximates the area under the curve, right? And we looked at pictures like this one, right? Here's our old friend y equals x squared plus 1, and here is a right Riemann sum with 4 approximating rectangles, right? And the idea is that the areas of the rectangles approximate the area under the curve, and it looks like more rectangles gives a better approximation. Okay, so we will define, since it looks like the Riemann sums give a better and better approximation as the number of rectangles grows. In calculus, when we have a sequence of approximations like that, where the approximations get better and better as one parameter goes in a particular direction. In Calc 1, the slopes of the secant lines became better and better approximations to the slope of the tangent line as h or delta x went to 0, depending on the notation that you used. Here, the parameter that needs to approach something is the number of rectangles, and what has to happen is it has to get bigger. At least that's what it looks like. So it makes sense to define the limit as n goes to infinity of this Riemann sum as kind of the thing that we're after, right? That's the limit as these approximations get better and better and better and better. We'll call that thing the definite integral of f of x from a to b, and we'll use the notation you see highlighted in blue. So that elongated s on the far left is an integral sign. The s is meant to evoke a sum, which is where the integral comes from, right? It's the limit of Riemann sums. And of course, we have the function. Inside, we need to know what function we're talking about in order for this to make sense. And then the endpoints of the interval are sort of at the bottom and top of the integral sign. The dx is kind of a relic. This is notation that was used in the mid-17th century when integrals were invented. And so we're sort of stuck with it. It's not really necessary, but so it goes. Okay, so this is how we will define, the definite integral. And the first thing that we should notice is that when building this Riemann sum, we actually don't care whether the function is positive or not. We can make a partition, we can compute delta x, we can pick the evaluation points, and we can plug them into the function whether the function is positive or not. So here's what that looks like for a function that's not positive. And let's maybe look at fewer rectangles, right? So here's a Riemann sum. Let's go up just a tiny bit from there. Here's a Riemann sum for the function f of x equals 1 minus x squared. you can see them on the interval from 0 to 2, right? The left endpoint is 0, the right endpoint is 2, and this is a right endpoint approximation, and that's easiest to see maybe over here on the left, where you can see for each rectangle, I draw the top of the rectangle by using the function value at the right end of the subinterval that the rectangle sits on. Now over on the left, this is all kind of as it was before. We've seen this kind of picture. But over on the right, notice what happens. The function is now below the x-axis. Well, that happens sometimes. And I can still evaluate the function at the right endpoint of the interval, right? Look at this rectangle where my cursor is right now. But notice that the function value at the right endpoint of the interval is going to be negative now. And that means that in this sum, the function value will sometimes be negative, right? It'll be negative whenever the function is below the x-axis. Delta x is always going to be positive. It's a width of a subinterval. So what happens when you build a Riemann sum in a case like this is all of these terms in the Riemann sum, the terms corresponding to the first 5 rectangles, are positive, but the terms corresponding to these rectangles are negative. And of course, you'll get some cancellation with the positives and the negatives. So what are we approximating here? Well, let's turn up the number of rectangles. The positive terms approximate area the way they always do. And the negative terms, well, they're kind of approximating area, except they're negative. It's just that their sign is wrong. So what's being approximated here is a quantity that we will call net area. So the net area, right, so net purple area, I guess I call it here because that's the color in the picture. The net purple area, or the net area, is the area above the x-axis minus the area below the x-axis. So we have to be careful of terminology here. Area is never negative. It's a positive quantity by definition. Net area is something a little bit different, and net area could be negative. Looking at this picture, for example, it looks like the stuff below the x-axis is a little bigger than the stuff above the x-axis. So my bet is that this net area will come out to be negative, although that remains to be seen. And the definite integral is calculating net area, not exactly area. So this is a little bit of a subtle point. Integrals are closely related to areas, but they're not automatically areas. They're equal to net areas. If the function never goes below the x-axis, like this one, of course, there's no difference between area and net area. So here, the integral will just compute the area under the curve as designed. But this is kind of good news that even if the function goes below the x-axis, the integral still has a nice geometric interpretation. It's just not just sort of a useless exercise in building this big sum and taking its limit. When we get the result has meaning. Okay, there we go. Yes, this sentence is exactly what we were just saying, right? The integral measures the net area between the graph of the function and the interval AB. And when I say the interval AB, I mean on the x-axis. All right, so let's look at a few examples. Suppose that we were to compute this integral. By the way, how to compute an integral is a question that we're mostly punting on for now, but we'll certainly come back to it. For now, this is mostly a symbol. And if we had to compute this thing, what we would have to do is build a Riemann sum and take the limit as n goes to infinity. And we'll do an example like that soon. However, I can draw a graph of this function, right? So here's the function y equals x minus 3. This function, this function, by the way, is called the integrand, right? So the function that is inside the integral notation is called the integrand. So when I draw this function, the orange interval is the interval from 1 to 3, right? Those are the limits of integration. 1 is called the lower limit of integration. 3 is called the upper limit of integration. I can see from geometry what this integral is going to compute. It'll compute the area of this orange triangle, but it will be negative because it's below the x-axis. And of course, I can figure out the area of the triangle just using 1/2 base times height. Here is the area of the triangle, and the integral will compute that negative, so this integral will come out to be -2. Again, we would never say an area was -2, but the net area between this function and the x-axis is negative because the function's graph is below the x-axis on the interval. Here's another example. So now my function is f of x equals 10 minus 2x, and the interval is from 1 to 7, and the picture is drawn just below it. Here's x equals 1 over here where the cursor is now. Here's x equals 7 over here on the right. And again, I can visually see what the integral will compute. It will compute the difference between this area, which it will count positive because it's above the x-axis, and the green area, which it will count negative because it's below the x-axis. Again, I can use geometry in this case to figure all of that out, right? The area of the orange triangle is this, 1/2 base times height, right? The base of the triangle is from 1 to 5, that's 4 units, and the height is 8. I can get that by plugging x equals 1 into the function. 10 minus 2 times 1 is 8. And the area of the green triangle is given by this quantity. And so I take orange minus green and I come out with this value for the integral. And again, what 8 is it's the net area between the function and the x-axis. I would point out, by the way, that in these two examples, we're calculating integrals using sort of a cheat. That is, I'm calculating integrals by using the fact that I know how to compute the area of a triangle. And that's fine, but the whole reason we developed integrals was to compute integrals we didn't already know how to do, and triangles were one that we did already know how to do. So these are really for purposes of illustration. Okay, so how would I compute this area that is shaded in the picture here, right? So you see the function is y equals x squared minus 3x plus 4. Notice that the question is asking me to compute area, not net area. So I don't want to just take the integral of the function from 0 to 6, because if I did that, I would get this area over on the right minus this area on the left, and that's not going to give me the right value. Rather, what I'm going to have to do is split this up into a couple of pieces. Compute the integral from 0 to 4 of the function. Now again, how do we compute that integral? That's a question we're mostly punting on for now. We'll come back to that soon enough. But suppose we knew how to compute this integral. What this would give us, it would give us this area, but negative because it's below the x-axis. But the number would be right, the sign would just be wrong. And then if we integrated from 4 to 6, we would get the area of this right-hand piece over where the cursor is now, and that would come out positive because the function's above the x-axis on that interval. Well, now I know how to piece these two things together to give me the area I want. I take the right-hand integral, which gives me the area, and then I take the left-hand integral, make it positive, sort of take its absolute value, and add it to the right-hand integral. Or another way to express that is I take the positive integral and I subtract the negative integral, right? When you subtract a negative, of course, the negatives cancel and you wind up adding, right? So this will give me the orange area. Again, not the net area, but the area. Okay, so let's do one example where we actually compute an integral. Most of this little section is about understanding the relationship between integrals and areas. Computing an integral for us right now is difficult until we get to the fundamental theorem of calculus, which you can see at the bottom of the screen is coming soon. Well, this is by definition the limit of Riemann sums. So the first thing we have to do is build a Riemann sum. We know how to do that from the previous section, right? So I'm going to take my interval from 0 to 2 and build a partition. Each subinterval will be 2 over n units wide, right? B minus a over n, which is 2 minus 0 over n, or 2 over n. Okay, so my partition points, hopefully that's what comes next. Well, I start at the left endpoint, 0, and I take steps of size delta x, just as we did before. What's different in this example is that the step size has an n in it, right? We're not using sort of a numerical step, but a variable step size. So the first step goes from 0 to 2 over n, and then I take another step of size 2 over n. Now 2 over n plus 2 over n is 4 over n, and that's where that comes from. And then I take another step of size 2 over n. 4 over n plus 2 over n is 6 over n, and so forth, right? The next one would be 8 over n, and then 10 over n, 12 over n, and so forth. Notice that the kth one, this might be worth doing. The way I get the kth point is I do, whoops, that's not what I want to do. Well, all right, let's just do this, is I do 2k divided by n, and so I'm going to need an ellipsis here. There. right? Because here's the first one, 2 times 1 divided by n. The second one is 2 times 2 divided by n. The third one is 2 times 3 divided by n, and so on. All right, let's put that away. All right, so let's see if we can build our Riemann sum. I think we'll do a right Riemann sum here, right? I'll use right endpoints as evaluation points. And that means here's the first subinterval, right, from 0 to 2 over n. The right endpoint of that subinterval is 2 over n. So that's the first evaluation point. And the second subinterval is here, right, from 2 over n to 4 over n. The right endpoint of that subinterval is 4 over n. Third subinterval, 4 over n to 6 over n, right endpoint is 6 over n, and so forth, right? So here are my evaluation points. When I use right endpoints, the evaluation points are basically the same as the partition points, which is kind of nice. I don't have to do a lot of new figuring. All right, so let's build our Riemann sum, right? It should be f of c1 delta x is the first term, f of c2 delta x is the second term, f of c3 delta x is the third term, and so forth. The kth term looks like this, right? F of ck times delta x. Again, if this is going fast, of course, just pause the video, stare at it for a little bit, and then come back to it. Okay, I'm going to put this in summation notation. I mean, summation notation was made for this, right? I've got this big, long sum with a lot of terms. The terms have a pattern, and this is what the sum looks like, right? It's f of 2k over n times 2 over n. Here's the kth term over here. All right, well, f is not an abstraction here. It's the function x squared plus 1. So f of 2k over n is 2k over n all squared plus 1. And notice that 2 over n is a constant with respect to the counter, right? K doesn't show up in the quantity 2 over n. So I can pull that constant outside the summation. That's one of our properties of sums from the very first section. All right, from here, it's a festival of algebra. So when I square this quotient, excuse me, this fraction, I square the top and I square the bottom, right? So 2k all squared is 4k squared, and then n squared is n squared, like so. And then I'm going to split this sum up and factor out constants, right? So when I have a summation of a sum, I can split it into two separate sums. The first sum will have this as the term, the thing that's highlighted in blue. The 4 and the n squared can pull outside because they're a constant. And in the second sum, I just have 1. The 2 over n, notice, is multiplying the whole thing. So I'm going to have a 2 over n in front of each summation. All right, now hopefully you remember that we have a formula for the sum of the first n squares. You can go back and look it up, and it turns out to be this thing right here in blue. And of course, if you add 1 to itself, n times 1 plus 1 plus 1 plus 1 up to n just gives you n. This quantity here, when I multiply straight across, right? 2 times 4 is 8, n times n squared is n cubed. That's where the 8 over n cubed come from. More algebra, right? Multiplying a bunch of stuff out there, and the n's cancel in this term. And the reason for doing this is what I want to do is compute the limit as n goes to infinity of this thing. And now I'm in a position to do that, right? Hopefully you remember from Calc 1 that a rational function like this, right, that first term is a rational function. As n goes to infinity, a rational function goes like the ratio of its leading terms. And the leading terms are 16n cubed and 6n cubed, right? The leading terms are the terms with the highest power of n. And so that limit comes out to be 16 over 6, right? Ratio of the leading terms. And of course, the limit of the constant 2 is just 2. So I get 16 over 6 plus 2, and when I do a little arithmetic, that comes out to be 14/3. And we have computed our first sort of non-trivial integral. Indeed, this was the integral I believe we were approximating back in the Riemann sum section. Let's go back in time. Here, where are we? This area right here, right? And you'll recall that we did this crude estimate of 5.75 for the area. Well, it turns out the exact value of the area is the number that we just came up with, which is way, way down here. Here it is, 14/3, right? So that is 4 2/3, so like 4.67 is the exact value. Okay, now you will observe, and many of you have probably seen enough calculus to know that this is hard. That is, this is quite a computation for what should not be a super complicated integral. X squared plus 1 is not a really complicated function. So one of the things on our to-do list will be to develop a more efficient way of computing definite integrals. That said, it turns out that Riemann sums are indispensable for reasons that we will discuss later on. However, we will have better ways of calculating integrals. Okay, so that's good for this section, the relationship between integrals and areas. Be well, everybody.